In today's lesson, we are going to be looking at our third type of distribution. So we've already looked at uniform distribution and binomial distribution, and today we're going to be looking at hypergeometric distribution. So similar to the previous two, we are going to be involving concepts that we've already looked at previously and just applying them to the idea of distributions, which is essentially just looking at the probability for all of the possible outcomes, as well as calculating the expected value. So before we get into it though, let's do a little bit of a review of what we've covered. So the forecast calls for a 35% chance of snow on any given day in December. And we want to show the probability distribution for those days. So we need to create a table. We don't have to, but it isn't, well, we do have to because that is how we kind of organize it, because we have to look at each specific outcome for our random variable. And our random variable is the number of days that it could snow. And then as well as looking at the probability of those outcomes. So the first one, right, we have 31 days in December. So we have a chance of 0 snow in general. Or 1 day it snows, 2, 3, 4, 5, and so on, all the way up to 31. Right, we have 31 days, so there's anywhere from 0 to 31 days where it could snow, or of days of snow that we could have. Again, for our probability distribution, because it's a binomial distribution, because again, it is independent events. If it snows one day, it doesn't affect the chance of it snowing the next day. And there's either a success or fail, snow or no snow. We have the independent trials. So we need our probability of success, our probability of failure. In this case, success, looking for days of snow, 35% or 0.35. Probability of failure then, or in this case the opposite, so no snow, this would be 0.65. Again, remember our formula, n choose x times p to the power of x times q to the power of n minus x. So for 0, we have 31 days in December, choosing 0 of them, multiply by 0.35 to the power of 0 times 0.65 to the power of 31. The next one would be 31 choose 1. 1 day in December, 0.35 to the power of 1 times 0.65 to the power of 30. And again, I could go through and do all of this. We'll skip to the last one. 31 choose 31. So we're assuming all 31 days there's going to be snow. Multiplied by 0.35 to the power of 31 times 0.65 to the power of 0. Right, so the exact same formula, just changing a couple of values there, the exponents and how many items we're choosing, or in this case, how many days we're choosing. So that would give us the probability distribution. And B, we want to determine, okay, what is the expected number of snowy days this December? Well, we could go through and do the sum of each value or each outcome multiplied by its probability, add them all up. However, there is an easier way for binomial distribution, which is just n times p. So in this case, there's 31 days multiplied by 35%. And we get 10.85. So basically we would expect 10.85 days in December to snow, or there to be 10.85 days of snow. As a warm-up, going into our new type of distribution, let's take a look at a class of 25 students. 15 of them have a driver's license. If 5 students are randomly selected, how could we determine the probability that one of these students has their license? What about 2 of them? So there's a couple of things we have to consider, and we've done similar questions to this. Right, so let's go through our scenario and kind of maybe underline what's important, because there's a lot of stuff here. So first, we have a class of 25 students. That's the total number of people. We have 15 of them that have a driver's license. So 15 have a driver's license, then that would mean 10 do not. We're also saying if 5 students are randomly selected. And then we're asking, what is the probability that one of these students has their license, or 2 of them? So this is going to be a probability similar to what we've done before. And we have done questions like this. So again, remember probability, we're looking at 2 parts, NA and S. In this case, NS might be easier to solve for. What are we doing in general? Well, we have 25 students, and we want to choose 5 of them, or 5 of them are randomly selected. Doesn't matter what order, we're just making a group of 5 from the 25 students. And A, the probability that one of them has their license. Well, there's 2 parts then to this group of 5. The ones that have their license, 15 choose 1, so they have their license. I'll put the complement, they don't have their license. So we're multiplying it by 10 choose 4, because they'd be the 4 remaining people in that group. So we put this together, probability of one person having it, 15 choose 1 times 10 choose 4, divided by 25 choose 5. This gives us 0.059. or 5.9%. If we were to do the same thing with 2 people having their license, what would change from above? Well, the bottom would stay the same because we're still doing the same thing. In general, 25 people choosing 5 of them. On the top, though, I'd be choosing 2 people from the 15 instead, and only 3 from the 10. Because now 2 people have their license, so 2 of the 15, and then 3 of the 10 for the remainder, or the ones that don't have their license. And this would give me 0.237, or 23.7%. And now if we wanted to, we could look at 3 people of the 5, 4, or all 5 of them having their license. So this idea here, this is an example of what a hypergeometric situation is, or distribution. So again, some characteristics or key characteristics. Hypergeometric distribution involves dependent trials, each with a success or failure as the only possible outcome. So in the one we just looked at, they either had their license or they did not. The probability of success changes for every trial because no repetition is allowed. Because we're selecting a person or we're picking a student in the previous example, the probability would change. Or change from trial to trial. And the random variable is the number of successful trials. So again, that part is similar to the other one that we've looked at. This one's different because now we're looking at dependent trials with only success or failure. So, long formula, these are essentially the 2 same things. Right? So it could be one or the other, just 2 different notations for combinations. Now it looks messy, but if you look at a question or you read a question that's hypergeometric, right? We've done questions like this. We've done probability questions like this. This is essentially a combination probability question, right? So even though this formula looks very messy, it might look very confusing with all the variables, we've done questions like this. So if you don't want to specifically stick to this formula, then just solve the problem like you would a combination type question. If you want to stick to the formulas, which you would be doing anyways, A is equal to the total number of successful outcomes. X is equal to the number of actual successes. Right, so that's our random variable. So in the car one, how many students that we're selecting that have a license. So 0, 1, 2, 3, or 4, or 5. R refers to the number of dependent trials. And N refers to the number of total outcomes. So we've done this before. We're going to go through and look at how to basically use that. Again, we also are going to be looking at expected value, right? We talked about how we can have how we can find or determine the expected value of a probability distribution. We could go through and use that standard form that we did before, right, which is the sum of each value multiplied by its probability. However, we may not want to have to always do that, right? Maybe we're only concerned about the expected value and not the actual distribution itself. So if we have a hypergeometric distribution, we could use this formula EX, where the expected value is equal to RA divided by N. R is the number of dependent trials. A refers to the total number of successful outcomes. And N is referring to the number of total outcomes. So let's go back and revisit that warm-up. So let's use our formula to kind of help us with that, right? So again, we're looking for a success, which in this case is having a license. If we're using that specific formula, which was A choose X times N minus A choose R minus X, all divided by N choose R. A in this case was the number or the total number of successful outcomes. This would be 15 because there's a total number of 15 students that have a license. X would be our actual possible outcomes, the actual number of successes. So that's anywhere from 0, 1, 2, 3, 4, or 5. N is the total number, so 25. The total number of outcomes, there's 25 people. And R is the number of trials. This is 5, right? Because we're choosing 5 people. So if we wanted to go through and actually calculate each one, right, you could think of it as using this formula, or again, think of it as a combination probability question, right? So 0 people, selecting 0 people that have a license. So 15 people choose 0 times, then there are 14 people, or sorry, not 14, 10 people choose 5 divided by 25 choose 5. You can see how we're getting these values. So the first one, 15 successful, total successful, choosing 0 of them. And then for the next one, we would take the total number, which is 25, minus 15 to get us 10. So we were already doing this formula when we were solving these types of questions. That's why I said you can kind of just focus on it as a combination question rather than using this formula, because it might be easier to kind of think of it that way. For 1, we have 15 choose 1 times 10 no licenses, choosing 4 of them, divided again by 25 choose 5. I'm going to zoom in to make it a little bit easier. Next one, 15 with licenses, choosing 2 of them, times 10 without, choosing 3 of them, all divided by 25 in total, choosing 5. 15 choose 3, times 10 choose 2, over 25 choose 5. Again, I'm not going to go through and actually find, or I'm going through this calculation over and over again, just so you have that kind of repetition, so you can kind of see how it plays out, or how it works. So 15 choose 4 times 10 choose 1, divided by 25 choose 5. And finally, 15 choose 5 times 10 choose 0, divided by 25 choose 5. And you can see how it's the same formula, similar to binomial distributions. It's the same formula, we're just changing small pieces as we go through. One thing you could think of it as, the first one, we're looking at how many ways can we choose the successful outcome or the success. And the second part is looking at the failure, right? So each kind of combination or each probability should have those two components, a success and a failure component that we're multiplying together. Again, we could go through and find the actual probabilities. I'll write them down quickly just so that if you are trying this at home, you do practice using your calculator just to make sure that it does work, or that you can enter these types of questions or formulas in properly. So those are the probabilities for each of those possible outcomes. Now, if I wanted to find the expected value, I could go through and do 0 times 0.0047, 1 times 0.059, right? This would just be 0.059. And I could do that for the rest of them and then add them up. However, again, if I'm only concerned about the expected value, this is a lot of work. So what I could do instead, I could just do that formula. The expected value is equal to RA over N, right? So the number of trials, so 5 times the number of successes, 15, divided by the total number of options, 25, which gives us 3. So we would expect to have 3 people, or in our group of 5, we would expect to have 3 students that had their license, right? Which kind of makes sense. We look at our probability distribution, it is the highest, right? So that might be what we expect happens. So let's recall a little bit going back to combinations, because again, this is kind of a combinations question. In Lotto 649, 6 numbers are chosen at random from 1 to 49. How many ways can you choose your numbers? So again, in total, we have 49 numbers, and we're choosing 6. So we have 49, choose 6. To win second prize, you must match 5 of the 6 numbers. How many second prizes are possible? So again, we have to look at 2 components. We have to look at our winning numbers and our losing numbers. Now we might also consider this a success and a failure. So how many winning numbers are there? Well, there's 6 of them, and I'm choosing 5. And I'm going to multiply that by the losing numbers, which is 43, choosing 1. Right, so again, similar concept, but hopefully now you can kind of see the connection to hypergeometric. What is the probability of winning 3 numbers? Well, very similar to what we did. Let's look at our success, which is a winning number, and our failure, which is our losing numbers. So I have 6 winning numbers, and I'm choosing 3 of them, multiplied by the 43 losing numbers, choosing 3 of them. And hopefully we can see that connection from that actual formula. A, choose X, times N minus A, choose R minus X, all divided by N, choose R, right? So if we were to look at this, we'd have 6 total successes or possible successes, choosing 3 of them, times 49 minus 6, the total number of outcomes minus the total number of successes. 49 minus 6, that's where we get our 43 from. And then R, the number of trials, so 6 minus the 3. So 6 numbers in total that we're selecting, minus the 3 successful outcomes that we're looking at. That's where we get the 3 losing numbers that we're choosing, all divided by 49, or if we turn it to probability, all divided by the 49 total numbers, choosing 6 of them. So hopefully, again, we can see the connection between the combination questions and the hypergeometric distribution. So example 2, determine the probability distribution for the number of women on a civil court jury where there are 6 jurors selected from a pool of 10 men or 8 men and 10 women. So we have to think about, okay, what is our successful outcome? What's a success in this case? Well, success in this case is selecting a woman based on our scenario. So that's going to help us find our other possible values, or at least think about our different combinations or different groups. So if we're going to go to our formula, A is 10, which is the total number of women, or the total number of successes. X is our actual number of successes. So in this case, we could have anywhere from 0, 1, 2, 3, 4, 5, or 6 women, because there are 6 jurors that could be selected. So these are all our possible successful outcomes, or possible number of women. N is going to be 18. N is the total number of possible outcomes, right? So this is the total number of people. And then finally, R is equal to 6. This is our number of trials, or in this case, the number of people being selected. So number of trials, or in this case, selections. Right, so these are all the values that we're going to use. So if you prefer the more kind of clinical way, I guess, of solving it by using the formula, this is what you would use. And you would go through and do this different times, or 7 different times for all the possible outcomes. Again, you can also just use kind of the idea of thinking of it as combinations. Think of your 2 groups, your successes and your failures, the women and then the men. So different ways you can think of it. But for the first one, you should have 10 choose 0 times 8 choose 6 divided by 18 choose 6. That would be the first one. The second one, 10 choose 1 times 8 choose 5, all divided by 18 choose 6. And we just kind of repeat that going down for the different outcomes. So again, you can go through and fill out the rest. I'm just going to use technology to kind of skip us ahead a little bit. So we have all of our probabilities here now. Again, we could go through, so this would be 1 out of 153, 25 out of, I believe it is 306. So actually both of those were incorrect. So just quickly, these are the correct probabilities. If we wanted to, again, we can then go through and create a probability distribution graph, right? Looking at the outcome on the bottom on the x-axis, or number of women that we could select, and then the probability is always on the y. So again, if we wanted to, so 0.1 or 10%, 0.2 or 20, 0.3, 30, 0.4, 40%, 0.5 or 50%. Right, and we can have anywhere from 0, 1, 2, 3, 4, 5, or 6 women. Right, so looking at 0, it is 0.15%. So this is going to be kind of relatively small. That's probably bigger than what it actually is, but our graph doesn't have to be 2 to scale here. 1 is about 3%. Change that first one to almost just a line at the bottom. 1 is 3%. 4 or 2 is 16, 17%. Here. 3 36%, 4 is 31, 5 is 11%, and 6 is about 1%. So this is what our probability distribution looks like. And again, it just allows us to visualize the different probabilities so we get an idea of which one is most likely to occur. We just kind of see how everything is just distributed. We could also go through and calculate the expected value in this case. Right? We could go through and do the entire x times px if we really wanted to, but to save some time, because again, that can be very time consuming, and especially if we're only asked what is the expected value, don't even need to do that table. So RA divided by N, so the number of trials in this case was 6, multiplied by the number of women that we could choose from, which was 10, divided by the total number of people, which was 18. We get 3.3 people. In this case, or 3.3 women. So we would expect that if we were selecting a group of 6 jury members, we would expect 3.3 women to be on that jury. Again, obviously, the decimal doesn't quite make sense, but when we're looking at a weighted average or an average, the decimal is okay. The last question, so we're looking at 500 raccoons are caught, tagged, and released into a wilderness area. Sometime later, 40 raccoons are caught and 15 of them have tags. We want to estimate the raccoon population in that area. Well, we're going to use our expected value formula to help us solve this question. So we're looking at 500 raccoons, 40 of them are caught, and 15 of them have tags. So in this case, we are looking at what is the expected number of raccoons that are being caught. So that is what we're given. We're given some of the information. Let's highlight the information that we're given. So we're given that 15 of them have tags, 40 of them are caught, and there are 500 raccoons caught, tagged, and released into the wild. So we want to estimate the actual population. So if we were to imagine going through and doing these trials, right, or doing this scenario as a hypergeometric distribution, we have our R, we have our A, and we have our N, and we have our expected value. In this case, we're looking for N. We don't know what the total number of possible outcomes are. Right? Again, remember, N is the total number. So that's the tagged and all the untagged raccoons in the wild. R is the number of trials. Right? So how many times did I select raccoons? Well, in this case, we selected 40 of them, or we caught 40 of them. So you could say we had 40 trials. A is the total number of successful outcomes. Well, what's a success in this case? Well, in this case, a success would be considered a tagged raccoon. So we have 500 raccoons that are tagged in total. The expected value is based on the overall population. What would we expect to get? In this case, we got 15. So based on getting 15 tagged raccoons from our sample or from our trials, what would we expect the population to be, or what could we assume the population is? So in this case, 15 is our expected value, is equal to 4 or 40 times 500, all divided by an unknown. So we can bring the unknown up, so we get 15n equals 20,000. 20,000 divided by 15, we get 1,333. So that means then, based on how many raccoons we got from our trials, or the expected number, we would have to then assume or estimate that the overall population is 1,333 raccoons. So this is a way that researchers actually do kind of calculate or try to estimate the actual population of animals in the wild, because obviously you can't just line them up and count them. So you'd have to kind of use this where we're making the assumption that the number of raccoons or the number of animals that have tags, that's our expected value. If we know how many we've tagged and released in the wild, then we can kind of estimate the actual population. Again, the main thing from this lesson is just being able to identify a hypergeometric distribution, use the provided formula, or refer back to or see the connection between combinations and hypergeometric distributions, and then calculate the expected value if needed. Again, if you do need to do this in a table, or for whatever reason need to do some sort of data analysis where you have to create this distribution, you can use Google Sheets to just come up with the formulas, or to enter a formula and just kind of drag and drop to fill in the rest of the table. But again, we're not too concerned about that. The main thing right now is just understanding hypergeometric distributions, the characteristics, the formula, and how to calculate the expected value.